in the color coding scheme. What the 666 machine, as I have named it, is it's a segment of 3 coil segments in series arranged circularly. So we can see that we got 1 to the left, now 1's in the middle, now 1's on the bottom. Likewise 2 does the same thing, likewise 3 does the same thing. The phases circle around each other. This gives the phases a change in induction due to mutual induction with the corresponding phases. And in finality, what we do is then reverse connections to each middle segment. This produces a 1/6 of a cycle difference between both the top and bottom segments, and it causes those fields on the outer 6 coils to be repelled into space, so that we're getting more amp turns of magnetic field in space by the middle segment, shoving those amp turns of magnetic field out. When this occurs 5/6 of the entire cycle, and we can monitor just one phase, look at the magnetic field by the scope, and then all 3 fields, look at the magnetic field from the scope, and we can see the magnetic fields out of the polar endings, the 6 polar endings, has been enhanced. This is the reason for constructing this system. Now after this, if the coils, middle segment coils, were not reversed, the inductance from each phase will be lowered. We do not want to do that. We want the inductance from each phase to grow greater. We want it to grow greater so that we can balance it out with the capacity and obtain a better Q factor. Our Q factor will be noted as the individual voltage rises on each phase with respect to the input voltage. Now what we're going to do today is show that what this causes at 1/6 of a cycle mutual induction. Nature works at 90-degree phase angle, induction-wise. But what we've done here is arrange something that's closer to 90 degrees. It's at 60 degrees, 1/6 of a cycle. This extra segment of induction causes a rotating voltage vector. This rotating voltage vector will increase the voltage 50% of the time, and it will decrease the voltage 50% of the time. And because of this, we'll see a fluctuating voltage output. Okay, after we have, I think we have explained everything about 666 machine. We have to do this repeatedly for people who have never heard of it. What we're going to do now is we've got inductors. We've got high turns amount 23 gauge inductors at 140 ohms, which translates out to about 2.4 Henry. Right now we have no inductors on the system. We want to look how balanced the system is. The system is very well balanced. Our stator line amperages are 0.47 amps, and below that we have the phase amperages attached in delta, and there's 0.278, 275, 277, and you can see the fluctuation of voltage caused by this rotating field vector. But we're going to look on the scope to see this rotating vector, which causes a higher frequency. It's actually a heterodyned effect, and we're going to see how we can obtain complete pulsed power by the principle by having that rotating voltage vector enhanced by mutual induction. Okay, to do this, we're going to start adding inductors to the system. Those are represented by the black checkers there, and the green one. The green one's going to go underneath on one ending of phase 3, and the other two are going to go on top. As such, and as such, and as such. Right now we don't have anything added. We're going to show the effects of the first edition. We have the scope set at 100 volts per division on the high probe setting. And here's our meterings. And here's the first edition. Here's the system from the side, showing the 3 inductors. As noted, we've got 3 inductors. These inductors right now, their pathway is broken so that no current can assume. So we assume then that the system is running free with no loads. Now watch what happens when we add the first inductor on top of phase 2. Typically what will happen for a single addition it will affect phase 3's amperage drop. On air core transformers such as this, you typically think in terms of loss of vibration, working completely opposite to the ferromagnetic transformer. We're looking for our amperage meters here. Because we get such a high voltage out of the system, when we do these tests, we start tests out without the alternator's field being turned on. Because we obtain some pretty appreciable voltages out of there, and it would be beyond the metered specs if we had a field turned on. So we're in the unenergized field state, so-called rotational magnetism state, or remnant magnetism, where we still get voltage and amperage out even though the field is not energized. Okay, we're going to add that inductor. Note the amperage on phase 3, 0.278. Note the phases 1 and 2 stayed relatively the same, but the amperage on phase 3 went down to 0.14. Now look at the effect on the scope. This heterodyned process, you can see a dip and a rise in voltage. This is set at a very low sweep rate, 1/10 of a second for a screen sweep, or 10 milliseconds per division. So we can see these effects of the extra voltage that is rotating in time. We can see that there's not much effect there because we don't have much of a dip. Okay, we're going to go over here and look. Then at our meterings, we're on top of phase 2. We have 153 volts generated by that inductor we just now hooked up. Now we're going to hook up the next inductor. Want to know we got 22.7 milliamps on that. And when we add the next inductor, the one behind it in this phase rotation, we're going to find a decreased amperage. Now we're adding the inductor over phase 1. What do we have here? We now have 2 inductors added to the system. This is the orientation that we use for the wireless Tesla coil. Note that even without the field turned down, we have generated some 320 volts between 196 volts and 149 volts. The 149 volts is coming from the back, the 196 from the front, and if you apply the law of cosines to that, you'll find out that's about 130 degree phase angle. It's not 120 degrees because the mutual induction between the systems has actually changed the phase angle. Now we'll go and look at our amperages. Note that now, instead of phase 3 being affected, it is affecting there's the 2 inductors on the system. There's the scoping on dual channel. And let us now note that on the back coil, this rotating field vector effect in time has become enhanced. We're now getting that. In the next step, we'll get it all the way to 0. And on our amperages, we're now below 0.14, 0.11, and phase 3 is back up towards its normal unloaded state. And we've looked at the interphasals generating that 320 volts. Now in finality, we're going to add the 3rd coil underneath, which will be that top one. We'll now be adding an inductor underneath phase 3. So we got coils over phase 1, 2, and 3. However, phase 3 was added from the bottom and not the top. Now we'll go and turn it on to the scoping. We'll go in there and add phase 3. Now that's showing a dual trace of 1 and 2. We want to see just number 2. There's number 1. There's number 2. At 10 milliseconds per division. It's providing complete pulse power now at this point. Finally, to end here, let's look at our amperage consumptions. Note that we started out with a 1 volt stator because we have an unenergized field, and those are 3 amperages, all of which have gone down from their unloaded state, and the system is unbalanced, of course. And here is a complete synopsis of the voltages on the system. On the bottom coil we have 137 volts. In the middle coil we have 133 volts. We measure 91 volts between them. We can form a phase angle from that information. That's the smallest phase angle. Our former phase angle now has become enlarged to about 150 degrees. We got 133, 100, and almost 233 would be 180 degrees, but we got 227. And lastly, the third phase angle, we got 220 volts between the 138 and the 133. So that pretty much shows that it's possible on a system like this to obtain pulsed power. Now the relevance to this may become into the future, where it may become interesting experientially if we can produce pulsed power at the resonant frequency of the Earth itself. Right now it's probably 19 hertz, and to make the system respond at 10 hertz, there's a lot of different things that we could do, but we're going to let that go for now and call this video quits.